Good afternoon, colleagues. Let me present to you a presentation on research and prediction of the stress-strain state of construction facilities in the undermined territories. Deformations of the Earth's surface in the territories of potash deposits occur for quite a long time. These times are calculated in decades. The process of deformation of the Earth's surface are caused by the shift of the soil mass layers that lie below the surface. Shifts in the layers of the soil mass are caused by the organization of mining workings. All this determines the pattern of the evolution of the stress-strain state of structures that are located in the undermined area. All this makes the task of studying the patterns of such behavior relevant. These tasks include predicting the evolution of the stress-strain state of structures, predicting the rates of deformation of the Earth's surface, and predicting stress relaxation in the ground mass. The solution of these tasks determine the stage of design and construction of structures in the undermined territories. Also, the solution of these tasks determine the pattern of monitoring the technical condition of structures that are already in operation. There are point objects and there are large arrays of structures such as residential areas and entire cities. The processes of deformation behavior of such types of objects differ significantly, which complicates forecasting. There are great difficulties with the analysis of the stress-strain state of objects that are made of different structural materials and built using different technologies. It's worth focusing on the fact that modern regulatory documents in the field of knowledge are significantly outdated. They do not take into account the latest technologies of construction and production of mining workings. These regulatory documents are based on research that was carried out in the last century. The methods of predicting deformations used in the documents do not meet modern requirements. Thus, there is a huge list of specific tasks united by a common direction. This direction is the safe construction and operation of various structures in the undermined territories. Based on field studies, we assume that a uniaxial deformed state occurs in the surface layer of the soil mass in the plane of the soil layer. The thicknesses of the layer is comparable to the depth of the foundation structures. This condition is caused by mining operation in the underlying layer of the ground massif. We also assume that the deformations in the soil layer are uniform in the first approximation. The component of this state can be accurately recorded by geophysical measurement tools. This state can always be represented as a field of major deformations in the plane of the Earth's surface. The structure rests on the described layer on the soil mass before the deformation process begins. We study the effect of soil mass deformation on the load-bearing elements of the structure. We determine the level of deformations in the ground layer, which corresponds to the critical state of the structure. Obviously, these questions are parametric in nature. They depend on the type of structure and its height, the type of foundation structures, the type of materials, the type of construction technology, the technical condition of the structure, and others. The answers to these questions are formulated in the space of the described parameters. The answers are determined on the basis of numerical solution of boundary value problems on the interaction of the structure with the ground mass. The simulation was carried out using the ANSYS software package. The simulation results contain information about the distribution of the parameters of the stress-strain state of the structure depending on the deformation of the undermined area. The limiting parameters of the deformation state of both the foundation array and the structure itself are determined. Reinforced concrete is a complex composite material. In engineering, there are no strength criteria that allow us to assess its stress-strain state close to critical, even when crossing this boundary. In our work, we had to determine the maximum level of the deformed state of reinforced concrete structures. In reality, it's quite far from the values that are laid down in the regulatory documentation. Therefore, we have developed a criteria that allowed us to approach the solution of the task. We have created a number of separate finite element models that simulate the behavior of individual critical components of structures. A very high level of sampling was set in the models. The solution was made in a physically nonlinear formulation, taking into account the possibility of cracks forming in the concrete body and plastic deformation of steel reinforcement. The decision was made taking into account the loading time. We selected a number of nodal points of the building and modeled the stress-strain state taking into account the deformation of the Earth's surface using the submodeling method. Our goal was to bring the stress-strain state of the catch to a critical state and surpass it. During the loading process, we were engaged in calculating of deformation energy in a representative volume of elements. Both concrete and rebar were included in the volume. We have constructed the dependencies of the deformation energy on the average compressive stresses in a representative volume and on the loading time steps. The slide shows the dependence of the deformation energy on the average compressive stresses in a representative volume and on the loading time steps. The dependencies are constructed for a representative volume of a critically load node of a reinforced concrete structure. We used this criterion as follows. We solve the problem of finding the limiting deformation energy for a representative volume of a node. Next, we calculate the deformation energy in the same volume, but in an elastic formulation for the same model. The graph shows how they differ. And then we talk about the mutual correspondence of the energies at a certain stage of loading. This is necessary in order to assess the condition of reinforced concrete units in the whole building, since the solution of the problem of finding the maximum deformations of the soil surface occurs in elastic formulation. This approach is somewhat crude and has a number of assumptions. These include the dependence of the deformation energy of the representative volume on the properties of concrete and reinforcement, on the percentage of reinforcement in the concrete body, and on the geometry of the node itself. But we have made the assumption that for these forms of stress-strain state and other things being equal, the deformation energies can be compared and brought into compliance with the state criterion. The criterion in this case is the work of external forces which is necessary for destruction in a representative volume. This approach requires further study and organization of a large number of field experiments. We are working on it. To test ourselves at this stage, we compared the values of the main stresses in a representative volume with the strength limits of a reinforced concrete structure, which are determined by the mixture rule for composite materials. This approach has justified itself. This slide shows picture of distribution of destruction zones in the volume of the model. This moment of loading precedes the complete destruction of the node. We mean that the node is no longer able to perceive the load. Further taking into account the calculated limiting deformation energies, we analyzed the behavior of various types of structures in the deformation zone of the Earth's surface. This slide shows the dependencies of the maximum deformations of the ground surface in the vicinity of building for different stores of monolithic and prefabricated frame reinforced concrete houses or buildings. The maximum deformations of the soil surface correspond to the previously determined level of deformation energy in reinforced concrete, which is critical. The graphs also indicate the border which is determined from the regulatory documentation. It can be seen that for different types of foundation structures there are big differences in the limit deformation both among themselves and from the standard value. It is safe to say that the normative literature requires correction. We see that for some types of buildings the limits can be increased, and for other they need to be significantly lowered. These results formed the basis of a newly developed regulatory document that is used by potash salt mining enterprises in the Urals. We analyzed the behavior of huge number of frames with different values of spans and different stores. Calculation were carried out for several large panel buildings. For each series of calculations, several dependencies are completed. In the maximum deformations of the soil surface in the vicinity of buildings and are determined. But the work continues further. There are a very large number of questions that require answer in the large and complex task. We are engaged in the development of a large direction in the field of operation and design of structure on part-time territories. There are also a large number of tasks in this direction that need to be solved taking into account modern technologies and materials. The task that we have presented in only a small part of this direction and requires development. The next steps that we will implement are the following steps. Clarification and testing of the strength criteria for structures based on the energy approach is required. It is necessary to conduct a large number of both numerical and full-scale experiments to determine this approach. It's of course potentially very profitable both from the point of view of numerical assessment and from the point of view of monitoring the technical condition of buildings. It is necessary to take into account the remaining components of the deformation fields in the soil surface. It is necessary to consider the problems of combining of field of deformations of the ground surface depending on the position of the axis of the building to the direction of deformation. It is necessary to take into account the rheological component of deformation process of such complex systems. An important component for the study is the study of vibration effect on structures in the field of deformations of the soil mass from micro-earthquakes and vibration caused by the development of the potash salt reservoir. It is necessary to create and verify systems for monitoring the stress-strain state of both structures and soil massives in the zone of the territories under development in order to predict negative process and ensure operation safety. Thank you for your attention, and now I'm ready to answer to your questions.